Good afternoon, everyone. My name is I'm a McNair scholar and civil engineering student at the University of Texas at San Antonio. And the topic of my research is the cracking behavior of high-strength spiral steel bar and concrete slab. This is a research that I conducted with my faculty mentor in the civil engineering department. His name is Dr. Wasim Ganu. So just a brief agenda of what I'm going to go over. I'm going to go over an introduction, give you a definition of high-strength spiral steel bar, and give you some background information, and go over the experimental program we developed and the method we use to test these bars, and also what are the conclusions that we observe. So when you walk around on a typical day, how many of you see these cracks on the pavement and around? That's pretty much, on a typical day, everyone sees that. What if you're taking a walk under a bridge and then you see something like that? Yeah, that raises high concern. As civil engineers, cracks is not allowed in our design. There are different places that you can see cracks, but as an overall design concept, cracks are not allowed. And so, with that, what is a high-strength spiral steel bar? A high-strength spiral steel bar, by definition, is literally a bar that has a yield strength of 72 KSI. By 72 KSI, I mean 72 kilopounds per square inch. So if I have a steel bar and I pull on it, and if the cross-section of that bar is 1 inch square, in order for me to create any permanent deformation, I would need to pull on that bar with a force of 72,000 pounds. That's a lot of forces, and that's why we use steel bar in reinforced concrete construction. So there are very economic and environmental advantages to using high strength. Mainly it's in the energy consumption. So the steel bar is a big industry that needs lots of energy and demands for primary resources, especially iron ore. So by using high strength steel bar, we're able to use less materials in our construction and still maintain the same safety in terms of construction. And also there are limited data that exists in building codes for concrete. So there's data that exists for the regular conventional bars, but no one has really explored what they use for high strength in reinforced concrete. So there are 3 current methods that are used currently in the production of high strength reinforcement, and the first method is known as microalloying. The second method is quenching and tempering, and the third method is cold rolling or cold working. And the bar that we used in our study were made using the cold rolling or cold working methods. And that method is basically when the steel is below the recrystallization temperature, you use this big roller to push the microstructure together, and then by that you increase the strength of the bar, but then you run into a problem that your bar becomes very brittle and you lose ductility and flexibility in the bars. So in the early 1970s, the ACI, the American Concrete Institute, which is the committee that maintains all the building and design codes for reinforced concrete, decided to set maximum allowable crack width in concrete. So what they decided was for any members that was exposed to the external environment, the maximum allowable crack width was 0.013. And for any member that was indoor, not exposed to the outside environment, it was 0.016 inches. If you try to make sense of this dimension, if you take a piece of paper, you fold it 2 times, the thickness that you get out of it, that's the maximum allowable crack width that is allowed in concrete construction. So if you walk around and you see cracks in the column, I challenge you to take a piece of paper, fold it 2 times, and if you're able to fit that paper in that crack, then there's a problem and you should let people know about it. So the reason why also they said it's allowable crack width is for aesthetic purposes. If you have a lot of cracks on concrete, it raises a lot of concern that people usually don't like it. And also for corrosion purposes, when you have cracks, water has the ability to penetrate and corrode the steel, you can eventually lead to failure of the members. So our goal was to investigate the mechanical properties of this bar and the performance in high strength in concrete slab. How do we do that? So we go back to the fundamentals. If in engineering, in your mechanical solid class, or in one type, you've seen this type of graphs, but if you're not, I'll try to go over it. And basically, you just look at this behavior. So steel has relatively two types of behavior. It has an elastic behavior and a plastic behavior. And the shape of these graphs matters. On the x-axis, we have what we call the strain, and on the y-axis, we measure stress. And that's how we're going to evaluate the behavior of these bars. Now, the problem that empirical data have shown that when you increase the yield strength of this bar, which is right here, so if you take this point here and you increase it there, in your reinforced concrete member, you have the tendency to have wider cracks when the member are deflecting. So that's a problem that empirical data have shown previously before. So for our test, we use monotonic tension test. And by monotonic, what I mean is, this is one of our specimens, and right at the center here, we have a load cell, and we load them at 1 point unit in the center, and we measure the deformation using strain gauges and different digital image correlation systems. And we tested total of 8 concrete slabs. 4 were reinforced with the regular deformed bars that are currently used in construction, and 4 were reinforced with the spiral bars that use 2 different diameters, the 5/16 inches and the 3/8 inches. So the first experimental result, going back to that graph that I showed you, if you look for the regular deformed bar that is currently used in construction, we saw that the first crack that we observed was almost around 4,000 pounds on our member. And as we kept on increasing the applied force, we saw that the bar fracture almost at 80%, 0.80%, we lost 20% of the strength in the bar. And we got a good deflection, drift ratio out of it. So the drift ratio is basically a ratio of the relative deflection in the member itself. For the spiral bar that we analyzed, we saw a similar type of behavior where the first flexural crack occurred at around 4,000 pounds, which is relatively the same. But what was important that we saw that there was a stable drift ratio. So if you look at here in the regular bar, the drift ratio is not stable. It's kind of like changing up and down. But for the spiral bar, it's a stable drift ratio, which is a good component and important for us because we want our members to deflect uniformly to let us know that something is going on, and we don't want it to just deflect, and then fail. So we want a warning before failure. When we look at the other type of regular deformed bar, the number 3 bar, we saw the same type of behavior, and the first flexural crack occurred around 3,000 pounds. And here we got a large deflection because these regular bar have a lower yield strength, so they're more flexible. That's why we're able to see a large drift ratio in these bars. When we compare with the spiral bar, because these bars were very brittle, we're not able to get a large deflection out of it. But in terms of strength and behavior, it was almost similar to the regular deformed bars. And looking at these cracks towards the end of the test, when you look here, you're able to fit a piece of paper easily in these cracks. And for the deformed bar, the failure, it was a big catastrophic failure that we observed. And that's due to the unstable drift ratio that we saw. And for looking at these cracks, the problem that we observed for the spiral bars is that we did not meet the maximum allowable crack width. So if you see the maximum allowable crack width were 0.016 and 0.013, almost at half yield point with the spiral bar, we're already exceeding the maximum allowable crack width. So that was a big problem in concrete design that we needed to take a next step and see how we can fix that problem. But when we compare with the regular deformed bars, you saw that we're able to meet the criteria set by the American Concrete Institute because these bars are being used currently. And the difference in cracks, there was a total of 86 cracks in the spiral bars and a total of 77 cracks in the regular deformed bars. And in terms of difference, that's not really a big difference because the difference of 9 cracks in one member is not really considerable. And looking at this the behavior overall, you see that there's a stable drift ratio here for your spiral bars, but for your regular deformed bars, you're able to get a large deflection and large strength out of it, but the drift ratio is not stable, which is a problem. when it comes to giving you a warning in terms of catastrophic failures. So in conclusion, we concluded that these large and high-strength spiral bar will exhibit wide cracks, but the crack in the concrete is independent of the concrete strength itself. So no matter what type of concrete that you use, whether it's high-strength concrete or normal weight concrete, the crack is mainly dependent on the type of bar, the yield strength of the bar, and other components such as the aggregate interlock and the type of the material that you use for the concrete. And also at higher stresses, your cracks will get wider for sure in the high-strength bar and both for the regular bar. In concrete, for the spiral steel bar, we saw that stable drift ratio is important to give us a good warning signal that our member is deflecting and we need to take charge and fix it. And finally, high-strength bars have the ability to reduce concrete congestion. So think of it, if I'm building a stadium, a concrete stadium, and I'm using 60,000 regular reinforced bar, and what if instead of using 60,000 regular reinforced bar, I use 30,000 high-strength bar and get the same behavior and the same type of strength? That's a big energy consumption save that you have, and also labor costs, because drawing a line on a computer as an engineer, you can easily do it, but somebody has to physically go on the field and put those bars in the right places for that member to get the forces out of it that you designed it for. So it's a big energy consumption save, and also in terms of environmental, we're able to decrease the resources that we use. With that, I would like to thank our UTSA Civil Engineering Department, our faculty mentor, Dr. Hossein Ganu, and the McNair Scholar Program at UTSA, and Mr. Darrell, Director, and you guys that pay attention to me. Thank you. Yes.
Okay, so would it be possible to go back to the slides?
Yeah.
I mean, to go back to the charts, the graphs. Because I'm trying to like sink it all in, but to me it was a little.
Which one?
A little back. The four ones, the isolated ones. Okay, those. Can you go to the first set? Okay, that one. Can you explain to me in layman's terms again the difference between, because I know you pulled out Young's modulus, like the theoretical kind. Yeah. But this one, can you just touch up on the difference between the FFC and the FY? Like, why was there such a big gap, like, in such difference? Because I've seen the little dots, but I can't tell which is which.
Yeah, so the difference in the gap is first, in the regular bar, you have the 60 KSI bar, you have a yield plateau. Okay. In the high strength bar, because of the production method that you use, the corroding method, that yield plateau is completely gone. Okay. So you observe it here. So when your bar yield here, you still have a plateau here. Right. But our bar are yielding here, and there is no relative plateau in these bars, and that's what makes that big difference. Okay. Yeah.
I have a question. On the first slide, I think when you talk about elastic versus elasticity versus plasticity of concrete, can you explain that a bit more? Like, how are these terms being used? Because we know like concrete isn't.
Yeah, so the elastic behavior, meaning that, so if I have a steel bar and I pull on it, before I can create any permanent deformation, my bar is still elastic. So if I pull on it and I let go, the bar is going to be able to recover all of its energy. And the plastic behavior just means that any more pull past the yield point, any force you apply creates a permanent deformation. So think of if you have a piece of plastic, you pull on it, and then you get to a point where whatever you keep pulling is just going and increasing that deformation. And that's the type of behavior that we observe. That's for steel. In concrete, steel behave the same way. So if you have a bar inside a reinforced slab, and as they're deforming, they're deflecting, and their cross-sectional area are changing with respect to the load that you're applying. And that's why we analyze this behavior, because that's how steel will behave in concrete as well. There's also more in-depth analysis relative to bonding of the concrete itself and the spiral bar.
Can you explain to me the two-factor stress? How is it like going away from the?
Oh, okay, so true fracture stress is basically measured instantaneously in the lab. So when you measure, that's with the assumption that cross-section remain plane. And your fracture stress is the engineering stress.
Yes.
It's basically when you're pulling on the bar, this zone that you see here, the necking,
Yes.
is that there's a point in the bar where the bar will fracture.
Yeah.
The size of the bar itself will start to get smaller and to neck. And that's why we take consideration of change in area. This is meaning that you're making the assumption your cross-section remain plane, but this is making the assumption that it's necking, so my area is changing.
So it causes buckling.
Yes.
Okay.
What are other types of steel bars that you could use?
So the other type of steel bar, they've been, with the process of making high strength, the microalloying is the most effective, but it's very expensive because you're adding different alloys like titanium, vanadium, to increase the strength. But there's been discussion who's going to put the money to find titanium and to find the vanadium. That's why people use the cold rolling method, because relatively all you need is the rollers to do it. But different methods of making iron is usually just carbon, adding carbon into the steel, into the iron ore, and that's how people have been, the production of steel has been made throughout the year. Yeah.
So is there like another phase of this project, or like where would you like to see this project go?
Yeah, so this project was divided into two phases, and we just finished the second phase. The second phase was to test splice bar. By splice, I mean, so if you're building a large column, we don't have steel bars that can span 100 foot. So what we use is you splice your bar together. So we tested splice bar inside reinforced concrete to see the behavior when these bars are spliced together. So you see it's spirally deformed, and in your regular bar you just get an X and Y Z reaction when you pull on it. But with this spiral bar you get an X, Y, and Z reaction, which is a big problem in bonding because the induced stress inside the concrete becomes large.
Last question.
Yeah.
Okay, so the spiral steel bar, is it favorable towards reinforced steel construction? Favorable?
Yes.
Okay.
Yeah, the nuclear industry actually in the U.S. wants to use spiral steel bar, but because the SCI doesn't have building codes and requirements for the high strength steel bar, that's why they cannot use it. But there have been, there's one faculty at Purdue University, Dr. Frosch. He's been working on high strength as well as trying to implement those codes into the American Concrete Institute. Japan has been using high strength steel bars in their design for the last 2 decades. So they've been advanced, and they use bars that are 100 KSI in the concrete design, especially for earthquake engineering.
Interesting. Thank you. Thank you.
But do not let the world's adversity either stifle your enthusiasm nor blind your vision. But the struggle towards excellence must ever be conducted on the high planes of self-confidence, a sense of purpose, and positive thought.